And our new unit is on work and energy with a little bit about power. So I'm not exactly sure how this unit is going to time out in terms of break and the end of the semester. I really don't know. Last year I broke it up into two different parts, but we weren't starting this until like when we came back from break last year, and then the second part I did in the beginning of second semester. So I don't know how it's going to time out. My hope is we'll get this whole unit in by semester. I'm pretty confident that we can do that. I'm just not sure if we'll kind of break it into some, like a smaller, like, test before break, and then another part where we put all the pieces together, like at semester exam time. I'm not really sure. So, to be determined, but we'll figure it out. So when we talk about this, we're going to start talking about work, is how we start this unit. So when we talk about work, work is when we expend energy to do something. We expend energy to do something. Now, that's a very general statement. What is something? And when we talk about doing something, we're talking about there being some type of movement or some type of displacement. So the kind of the classic example that we often talk about with work is if I'm going to go through, and if I push on this wall really, really hard, I'm applying a really big force. Get really, really tired. But the wall didn't move. So I expended energy, but I didn't actually accomplish anything. So I didn't do any work. Okay? So when we talk about work, and I often define that up in the top section right here. Today I'm going to do a little bit of writing on here, a little bit over there, a little bit over here, kind of going back and forth. So work is when we expend energy to do something. Okay, I have to do two things. I have to spend some energy, and we'll talk about what energy is a little later, in order to do something. Okay, in order to do something. On the board I have it written, but there is a generic, or a general, I shouldn't say generic, but general definition or equation that we can choose, or we can use to calculate the amount of work done by a system. Okay, so work is equal to plus or minus. These are the parallel. This is the math symbol for parallel, just like perpendicular. Parallel, that's what I'm trying to do there. So when we talk about work, it's parallel force times displacement. Okay, so quick to find these. W stands for work, and we measure work in the units of joules, or we can simply use an uppercase J. F parallel simply stands for some force that's acting parallel. So we just call it a parallel force. And then delta X is displacement. And this could be delta X or delta X or delta Y. So what's a parallel force? It's a force that's parallel to the displacement that you're looking at. There are four forces we're going to look at today. We're going to look at applied force, we're going to look at gravitational force, we're going to look at frictional force, and we're going to look at normal force. Those are the four forces we're going to look at. So we can take that general equation, and when we substitute a specific force into that equation, we get a specific type of work. And we'll talk about those four types of work. Now, if you notice in that equation, it says plus or minus. In math, I'm pretty sure every time you see a plus or minus, you guys, let me rephrase it, we have to make a choice. And we have to make the choice, is it the plus or is it the minus? So we have to go through, it's plus or minus, is one of the two. We got to do a little bit of like reevaluation, look at it a little bit different way to figure out whether it's the work of the plus or whether it's the minus. So when we talk about work being positive, negative, or zero, that's what I have on the board here. When we use that general equation, okay, we have to make the choice. So work is positive when, work is negative when, and work is zero when. So work is positive when the force, whichever force it is we're talking about, whether it's work, applied force, gravitational force, normal force, frictional force, when the force that you're looking at, when the force and displacement are in the same direction. Okay, so if I were you, maybe like right here would be a good spot to be writing that when, what is it, whether it's plus or whether it's minus. And hopefully there's a few other things we'll add to this, but hopefully we'll have enough space. If not, we can always put it somewhere else too. So work is positive when the applied force and the displacement are in the same direction. So if we were to take my cart, and if I push that cart in this direction, this direction, and if the object, I'm applying a force in this direction, and the cart is moving in that direction, the force, my applied force, and the displacement are in the same direction, then there's positive work being done on this cart because of the applied force. Okay, so if my force is to the right and my displacement is to the right, those are positive works. If my force is up and my displacement is up, same direction, positive, down, down, positive, left, left. Okay, as long as they're in the same direction, positive work. And positive work means we're adding energy to the system. We're adding energy to what we refer to as the system. Work is negative when the force, and whatever force we're looking at, applied force, gravitational force, normal force, or frictional force, when the force and, I don't know why I'm underlining and displacement are in opposite directions. Okay? When they're in opposite directions, then we have negative work, which means we're removing energy from the system. So if I'm pushing my cart this way, the applied force is in the same direction as my displacement. But if I'm looking at the frictional force, my frictional force is this way as I push the cart this way. Those are in opposite directions. So if my frictional force is in the opposite direction of my displacement, which you could say, well, isn't friction always in the opposite direction of displacement? Yes, good. We'll come back to that later. Then the force of friction is removing energy from the system. It's doing negative work. But we have to make that choice, whether it's the plus or whether it's the minus. Now there are 2 times when there is no work or 0 work being done on the system. And so this is really kind of meant to be a list, and then this got kind of low, so then I put number 2 here. Work is 0 when, well, remember, in order for this number to have some value, then we got to make sure we have some non-zero numbers here, because if we multiply by 0, 0 times anything is 0. So if work is 0 when the displacement is 0. So me pushing against the wall, I'm applying a force, I'm expending energy, but the displacement of the wall is 0, so no work is being done on the wall. The displacement is 0. So work is 0 when the displacement is 0. Or we can say that work is 0 when, I erased how I worded it last hour, but work is 0 when the displacement is not did I spell parallel right? Nope. No, I didn't spell that right. Error.
L's are supposed to be.
Wait, what? Yeah. Okay, sorry. Error. L-L-E-L. Thanks, everyone. That's kind of embarrassing. Okay. The displacement is not parallel to the force. And when I say the force, I don't mean Star Wars the force. I mean whatever force we're talking about at the time. So are we talking about the applied force? Are we talking about the gravitational force, normal force, or force of friction? Because they have to be both. There needs to be a force and there needs to be a displacement. Okay? So when we talk about what are the forces, the 4 forces we're going to talk about are the ones that I've mentioned, which is applied force, gravitational force, normal force, and frictional force. And because of those specific forces, we have 4 specific types of work. So if we use this general equation, we can talk more specifically about specific types of work. And there's a type of work that I refer to as work in. And it's really just saying, like, I'm putting some work into the system is how I use it. But that type of work deals with the applied force. So there's a little bit in between that I want to make sure we add. But if I'm talking about an applied force, I talk about work in. Because if I'm applying a force, I'm adding energy into the system or I'm removing energy into the system, I guess, which is kind of a backwards way to say it. But applied force is work in. So if we talk specifically about some parallel force, I'm specifically talking about the applied force. We still have to make the choice, am I adding energy to the system? Are they in the same direction, my displacement and applied force? Or in the opposite direction where we remove it, times a displacement. Now, something to note is in this situation with our applied force, this delta x could be either delta x or delta y. So we change that delta x or delta y to match the applied force. So for example, if I'm pushing my cart across the floor and I'm moving the cart in the x direction, I'm going to talk about delta x. But if I'm talking about me applying a force to this marker in the y direction, then I would use a delta y. So we choose the displacement that's parallel to the force that we're talking about. This one's an interchangeable one. If we talk specifically about the force of friction, then we can talk about the work being done by friction. So work is equal to plus or minus some force times displacement. My force of friction plus or minus displacement will give us the work done by friction. Is friction ever in the same direction as the motion of the object? No. We defined the force of friction as a force that opposes motion. So the work done by friction always is going to be a negative work. Friction is always going to be removing energy from the system, because no matter which direction if I'm pushing something this way, friction is going to be opposing. If this marker is falling through the air resistant form of friction is going to be opposing it in the opposite direction. So this is always going to be negative, because it's always taking energy out of the system. And then this is going to be times delta x. But just like applied force, that delta x could be either in the x direction or it could be in the y direction. Air resistance is an example of friction. We could have an object sliding down a surface. That'd be a little tricky in the y direction, because is it really sliding if it's almost free falling? I don't know, we'd have to think about that. But you change that delta x or delta y to match the force. So you make sure the displacement is parallel to that force that we're talking about. These two are the big two. There's two others we're going to talk about today, but probably after tomorrow we really don't mention them much, because there's other ways we can address those things. So these are the big two works that we're going to talk about throughout the unit. Over the next day or two, we're going to talk about these, but only for a little bit. The next force we're going to talk about is the force of gravity, because any object that has mass and is in a gravitational field has gravity acting on it. So our force of gravity is the parallel force we're talking about. So we choose the displacement that's parallel to the force that we're talking about. Well, gravity is always pulling straight down. So because of that, that displacement is always going to be delta y. Now remember, the work can be 0 on a system if the displacement is not parallel to the force. So if an object, for example, is being pushed to the right, the displacement is in the x direction, so my delta y would have a value of 0, so just something to keep in mind. But we have to make the plus or minus choice when we talk about the work done by gravity. Because depending upon which direction the object's going, gravity could be adding energy to the system, or it could be removing energy from the system. So it could be the plus. So if I take my water bottle, and if I lift my water bottle up, I'm sorry, that's the opposite. So if I take this water bottle and if I lower the water bottle, gravity is pulling it down. The displacement of my water bottle is also down. Gravity's adding energy, same direction, plus energy to the system. But if my displacement is up, but my force is down, then it'd be the negative. So we just got to make sure we assign the appropriate. If my force and displacement are in the same direction, my fingers are pointing in the same direction, then it's positive work. So in the case of gravity, the object would have to be moving down, because gravity always pulls down. But if the object's moving up, then gravity's working against it. There's another way we can address that type of work, and we will later. The last force, and this one we're going to talk about today and really tomorrow, and that's about it. This one is the work done by my normal force. And in our situations, this one's a little silly to think about. Or it's not silly to think about, it's kind of silly to use, because we never do anything with inclined planes. So our objects are always sitting on a flat surface, or they're sliding along a flat surface, because the normal force is always perpendicular to the surface. So in our case, our normal force is always straight up into the air. So it's going to be a delta Y. So if we were talking about my water bottle sitting on the table, there's a normal force up, and if it's just sitting there, well, it's not moving, so my displacement in the y direction would be 0. If I'm sliding this object to the right, my delta y is equal to 0. So what if I lift this water bottle up? Well, because of how we arrange things, and this is always 0, as soon as I get some displacement, as soon as my delta y is not equal to 0, it's no longer sitting on the surface. So for our sake, that value is going to be 0 joules, because as soon as I lift that object off the surface, there's no normal force. So my normal force goes to 0. Or if it's moving to the right, then my delta y is going to be 0. So it is one we'll talk about, but like I said, after like tomorrow, we're really probably not going to use that one. The two starred ones are the ones that we'll use longer term here. Okay, so these are the 4 types of works that we're going to start talking about. And we are talking in some pretty general terms, but we have to make the choice of whether we're going to add or remove the energy to the system by adding the positive and negative. All right, so let's go back to this sheet. This sheet has some terms and some kind of fill in the blank and kind of guided responses to help kind of reinforce these ideas. So, an impulse is a force acting over some amount of time causing a change in momentum. We'll come to that in our next unit. On the other hand, work is a force acting over some amount of displacement to cause a change in energy. Okay, so this is kind of our definition, right? Work is a force over some type of displacement that allows us to do or add or remove energy to the system. But in order for us to change the energy of the system, I have to have a force and I need to have some type of displacement. Okay, so this is just yes or no's with a quick explanation about whether force and a displacement occur, which then means we can work. So indicate whether or not work, the example represents work. So a teacher applies a force to a wall. So I apply a really big force, I'm exhausted. Okay, did I do any work? Why not?
There's no displacement.
Right. So no, because there was no displacement. Did I apply a force? Yeah. I tried really hard, but I didn't push the wall. So because there's no displacement, I didn't actually do any work. If a weightlifter takes a barbell or takes a weight and lifts it over her head, does she do work? Did she apply a force? Was there a force applied?
Yes.
And is there a displacement? So does she do work?
Yes.
Yes. both, there was a force and we had both a force and a displacement, right? We need both in order there for it to work. Now, if we take a moment and we think about that, so if she took a weight, she lifted over her head, she did work. But what if she sets it back down? What if we take something really heavy and we... Did I do work?
Yes.
What's displacement again? How far am I from my starting location? Oh, I didn't actually do any work again. So if I try it again, I'd have to, like, I don't know, throw the chair, I guess? I don't know. But if you think in the terms of definition of work, if you go to the weight room, almost, I can't really think of a situation that actually has work being done when you work out in the weight. Because we start and we end at the same locations, right? We take that stack of weights on the machine and it goes up and it goes right back to where it started. Or we, assuming we like put like bars back where we started, we start and we set them back down. We do the bench press, we take it off, we go down, we go up, and we put it back in the rack. But displacement means you need to apply the force, which I did, but we need a displacement. The displacement is how far are you from your starting location. Same thing, if I were to go for a 10-mile run tonight after school, if I start at my front door and I run 10 miles and end at my front door, my displacement, by definition, is 0. So technically, I did 0 work on my 10-mile run. Physics did a definition of work. Just something to think about. Waiter carries a tray full of meals across the dining room at a constant speed. The waiter, is there a force applied? And does the waiter move? So did the waiter do work? Yep. Yes. There is force and displacement. You try that last one quick. So if a shot putter launches the shot, did the shot putter do work? Yeah, they pushed, they applied a force, and the shot moved, so there was displacement, so therefore they did work. Definition, this is a definition thing. It's meant to be a multiple choice one. I'm just going to tell you right now that work is a vector. So there's 2 types of numbers that we've talked about so far this year, scalar and vector. And vectors commits crime with both direction and magnitude. However, when we talk about work, this one is a little bit different form of vector. So when we talk about a vector, work being a vector, we assign the positive or negative value, but we assign it based upon whether or not we're adding or removing energy. So when my force and displacement are in the same direction, I'm adding energy to the system, positive work. If my force and displacement are in opposite directions, then my work is negative and I'm removing energy from the system. So that's what those positive and negative signs mean for work, is whether I'm adding energy, positive, or whether I'm removing energy. That's going to be a negative. I forgot to mention, but just so you're aware, so here's your formula sheet that I passed out last unit. We're moving into, so here's your Fab 5 right here. This is where the first equation, right underneath the Fab 5, that's where that one is. And the 2 that we use a lot of, these are the 2 that I start on the board. They're listed on your formula sheet. So just so you're aware of those. work in specifically is plus or minus the applied force times displacement. Now that could be X or Y. Work done by friction is minus force friction times displacement, and that could be X or Y. Those other two aren't on here because, like I said, after tomorrow, we don't really talk about it much. So when we talk about units, the units that are associated with work, what did I say the unit that we're going to use is? Joules. Okay, that's the unit we're going to use. There's other acceptable answers on here, just for the record. I'm going to point out one, kind of two, and then there's even a few more. There's another like derived one. But if we look at our formula for work, work is a force times a displacement. And I'm saying a force times a displacement gives me work, which is measured in joules. So joules is a derived term, or a derived unit. So if we look at what two things we multiplied together to get to a joule, force is measured in newtons. Displacement is measured in meters. So the combination of newtons multiplied by meters, that's what gives us a joule. A joule would be defined as 1 newton of force for 1 meter. Right? If I apply 1 newton of force to cause an object to move 1 meter, that would be 1 joule. We are going to use joules. If we kind of follow that same rationale, this is a force times a distance. If we look at this one, well, this is a force, pounds, and distance is feet. So that's actually another term that we could use. We're not going to, so I'm not even going to circle it. And we could also, one of those ones on the far right-hand column is if we go back and define what a newton is, well, mass times meters per second squared, so kilograms times meters per second squared would also give us one, as long as we multiplied then by another meter. So I think it's that one, but I'm not going to worry about that. For number 5, we are looking to determine whether the work is positive or negative on the object. So remember, on the board I wrote it, and you hopefully wrote it down too, that if your force is in the same direction as the displacement, that's positive work. If they're in the opposite directions, that's negative work. If they're not parallel, so they're like perpendicular, well then that would also be a 0 work. So we have a car, so who's moving east, right? So if we just say north, south, west, east, car's moving to the east, car's moving to the east, and it skids to a stop. So if the car's moving this way, car's moving to the right, which direction is the brakes pushing on the car? Well, it's pushing in the opposite direction to cause a change in velocity or an acceleration. So if my displacement is to the right, my brakes are pushing to the left in the opposite direction. Those are in opposite directions, therefore that's going to be negative work. A freshman stands on their locker and they lift up to put something on their top shelf because they apparently have a really tall locker, or they're short, I guess. Freshman stands on his toes and lifts the civics book to the top shelf of their locker. The displacement, the delta y, is going to be up, right? And in order to lift that book, their force is also going to be up. Therefore, they're going to do positive work. They're going to do positive work. Why don't you try the next 3? Just for the record, the 4th one, it talks about a catcher putting their out his mitt to catch the ball, so they're going like this. Oh, to touch the baseball, that's what we're talking. The Six Flags roller coaster, they're lifting cars to the top of Goliath. That positive and negative work. Catcher pushes his mitt out to catch the ball. That positive and negative work. Falling parachutist opens their chute. They slow down. Is that positive or negative? All right, Goliath the car goes up the hill, and which way is that chain pushing or pulling? Up that hill. Okay, same direction or opposite direction? Same direction, right? So is that positive or negative work? Positive work. Positive work. If a catcher, this one maybe the idea is if a catcher pushes they're pushing their glove out, so their applied force is that way, and their glove moves that way. What is that, positive or negative?
Positive.
That's positive work. This parachute one is maybe a little bit. So if someone is falling through the air and they pull their parachute and their parachute slows them down, which direction is the person with the parachute going, up or down?
Down.
They're moving still downwards, right? Their acceleration is up, which is kind of weird to think about. Their acceleration is up, but they're still moving down. It's okay, that can happen. But which direction is the parachute's force, up or down? That force is going to be up. So then in this case, this is going to be doing negative work. All right, I want to try to get through these next three. So I got a few minutes. I think I can do it. So this one is talking specifically about applied forces. So when we talk about applied forces, we are talking about work in is equal to plus or minus the applied force times a displacement. Now this displacement could be in the x direction or y direction depending upon what we are talking about. But we have 100 Newton force is applied to move a 15 kilogram object horizontal distance of 5 meters at a constant speed. So if it's pushed to the right to cause it to move, which direction is this object moved? To the right or left? It's moved to the right. So when we talk about plus or minus, is the work in going to be the plus or is it going to be the minus? Applied force is to the right, displacement is to the right, that's going to be the plus. So then we take our applied force, which is going to be 100, times our displacement, and our displacement, our delta x was 5 meters. So positive 100 times 5, the work done is positive 500 joules worth of work. Now this one, there's two forces. This should say F1 and this says F2. It's kind of hard to read, but that's what it should say. So we're really talking about two different work ins, so I'm going to call it work in 1 is equal to plus or minus F1 times displacement. Now, if this is F1, which displacement should I be using? Delta X or delta Y?
Y.
Delta Y, yep. So this is going to be times delta Y. And my work in 2 is equal to plus or minus F2. And what's this going to be, delta X or delta Y? This is going to be times delta X. 10 Newton force is applied up and a 20 Newton force is applied to move a 15 kilogram object at a constant speed for a horizontal distance, delta X horizontal distance of 5 meters. So when I go through, what's my delta, if delta X is 5, what's my delta Y? If it moves 5 meters to the right, delta Y is equal to 0. So my delta Y is 0. So the work in done by force 1 is equal to 0 joules. Now, if my F2 is to the right, and my displacement is to the right, is this the plus or the minus? That's the plus. So my work in 2 is equal to plus 20 times 5. My work in 2 is equal to positive 100 joules. Oops, sorry about that. F2 is plus 20 times 5 for a positive 100. We're adding 100 joules of energy to that. I'll hold off on that last one. Just remember Mr. Rather's announcement earlier today reminding us that today is the last day of soft release. However, today is still a soft release. So we'll see you tomorrow. We'll pick it up from this choice. Thank you for your patience. I know this wasn't an exciting day, but I do appreciate your patience with it.